So WaveWatch is a package with a bunch of codes, and the main program is called WW3 shell, and that is the one which is calling the integration in time and the output and everything. And then I will also discuss briefly the pre-processing to get the input in the model and the post-processing to get the output out of the model, and issues with nesting different models together, and some final remarks. Okay, so before running the model, you have to define the model setup. Basically, the grid. And so the grid is both the physical grid, so in space, X and Y, or latitude and longitude, but also the spectral grid, because you have frequencies and direction of discretization. So WaveWatch is using a regular distribution of the direction. You just give it a number of directions. Typically, it will make the first direction. First direction in the code. It's trigonometric convention, so it's waves going to the east, and then it's marching like this. So you can have the first direction to be exactly at 0, or you can also shift it a little bit if you want by half a bin or a fraction of a bin. The reason for that is if you're using the first order scheme, it's actually better to shift the direction relative to the orientation of the grid. Otherwise, you have the accumulation of energy along the grid axis. And there was some funny results back in the 90s with people looking at 12 forecasts in California. There was always getting 12 from the south exactly along the grid lines, because somehow the energy was trapped in the one code along the north-south meridian. So after that, they're starting to shift things half a bin, and it already works better. So you can shift direction a little bit, and then the frequency choices, you just define the first frequency, the lowest frequency, and then the ratio of the one frequency to the next, so it's an exponential increase. Usually people use something between a 5% and 10% increase. If you use 5%, you're going to have a lot of frequencies to fit in your spectrum. So for example, if you start at a 35-second period and you want to go down to 1 second period, if you use an increment of 1.1, so 10% increase in frequency at each frequency, you can do that in something like 32 frequencies or 34. If you use a 5% increase, you're going to need twice as much frequency, like 60 something. So the cost of the model is going to be double. So this increment in frequency is important. What you would like to get is a good resolution at the peak of the spectrum, especially during a wind sea. And the problem is that the peak of the spectrum in the wind sea is like a transport spectrum, pretty narrow. And so if you use 10% increase, you only have like 1 or 2 points in the peak. But that's the compromise. So here, actually most of our application we use it with 10% increase. NCEP now is running operationally with 7% increase. That so means that they have 30% more frequencies. And so you define the grid with that. Then you're going to define some initial conditions. If your domain is not a global domain, you probably have some boundary condition, or maybe it's a closed base and you don't care. Then you need to prepare some inputs, and so all these different things are different programs that will be compiled separately, and you call them separately. And the actual integration of the wave equation in time is done by W3 shell for a single grid, or by WW3 multi for a multiple grid system. So when the model runs, then you have some binary output, and these binary output you typically want to post-process them in some readable formats, and so people at NCEP they use a lot grib. You can also use some ASCII output, but now here we all work with everything using NetCDF. So we have some post-processing with NetCDF. So instead of W3 outp, which is to post-process a spectra at some points, you can use OUNP, W3 OUNP, which is for NetCDF output, and the same thing. Instead of outf, there's an ownf, and instead of trck, which is for output along a track. For example, you want to follow a satellite track and get some spectra, or follow a ship track, or follow a glider track, or follow whatever track you want. You just give the position and the time. You can also output now with W3 TRNT with NetCDF output along the track. And you can also make some grib files. And yes, this is the NetCDF. Look, this is not right. Who wrote this? Roberto got it wrong. So it's not nested out here. Forget about it. Okay. Oh yes, and then there's some tools for regridding. For example, you have multiple grids and you want to put everything on the same grid with a given resolution. There's this www3dint to interpolate all the model results on the same grid. So for example, you have a global grid with regular grid, and you have a triangle mesh on the coast, and you can use int to put the triangle mesh and the global grid on the same regular grid format. This is for people that have tools only to play with regular grid, like in forecasting offices like that. Sometimes they don't have the proper software to play with triangle mesh. And this, oh yeah, www3 grid split, GSPL, is some automatic system for splitting a regular grid into many subgrids, doing some two-way nesting. So it's like domain decomposition, if you want, or parallel processing. So all of these programs, and those of you, I guess most of you who have been running WaveWatch, you know that they run their input from this file with an extension .inp. So the program W3 grid reads the input from a W3 grid.inp, and these files are ugly. And so we're slowly changing them to have some nameless instead of that. So we haven't finished that. So Mikel actually did all the code for W3 multi. So now you can run multi with W3 multi.nml. And we'll do that today or tomorrow. I don't know. What's it? Huh? Tomorrow. So you don't have to play anymore with the INP for multi. And hopefully by the end of the year, we'll have all the input files converted to NML. And so you don't have to worry about, oh, yes, I missed one line. And I don't know what this funny character I'm missing, or this, I don't know what to put there. Because that's a major source of headache. Yeah. But today you still have to use this. Okay. Right. And as I said, the first thing to do is to run www3 grid. Even if you run the model multiple times, like you're doing some forecasts for today, tomorrow, and so forth, you don't have to rerun W3 grid. What W3 grid does, it will generate a binary file called moddef, which is a model definition file, .w3. So all these model results have some .w3 extension. And this moddef file contains basically the bathymetry. Oh yeah, I didn't talk about this. Obstruction grids, which is some blocking factors for unresolved obstacles. Some masking, all the frequency grids, and some other parameters. There's also some pre-computed tables. Yes, there is a pre-computed table for SC4, which is taking forever to compute. So normally, you do it once and then it's done. If you actually want to test the model quickly, you can maybe it's better to use ST3 because the W3 goes much faster. What's happening with ST4? There's a crazy 3D lookup table which is computed, and that takes a few minutes. And yes, this moddef also contains all the parameter settings, so all the nameless parameters that you define to define the dissipation coefficient, the swell dissipation coefficient, and all these things are set up in this moddef file. All right. So, it also contains the time steps, the famous 4 times test we just talked about, and it also, yes, that's very interesting. It also contains information about input points. So if the model is expected to have some boundary forcing, it's also defined in that moddef file. And the ugly part of the nesting in WaveWatch, it also contains the output boundary point information. So imagine you start to run the Atlantic and then you want to do the Gulf of Mexico nested. The problem is that you have first to define where is going to be the Gulf of Mexico points for the nesting before you run the Atlantic grid. And that's a major source of problem. So we went around this, and because every time you do this, you're missing 1 point, or there's 1 point too much, or it's a nightmare. Instead of doing that, you can also output spectra point, like the usual output, and then you can use another program which is called www3 bounce to generate the boundary that will make the nest file for the other grid, and that makes it more flexible because you don't have to know in advance exactly what would be the final resolution grid. Yeah, for those of you that tried it, I'm sure that you know what I mean, but the other ones probably don't make any sense, but that's all right. Okay, so we have some data files. The input file, we run W3 and we get the output. So basically, you need to have the bathymetry grid. Okay. You can have some obstruction mask. If you don't have it, we can generate that with a MATLAB tool called GridGen. You can have the active, non-active point mask, and then all these settings, the parameter setting, everything. And then so these bathymetry obstructions and masks can be stored in this file, or they can be separate file, and then it's all combined in W3 grid, and you get the output with ModDef W3. So that's the first step. It's just defining the model configuration. And you don't have to do it for every run. You do it once, and then you can repeat. You can use this ModDef for all the other runs. Okay, so the model needs to have some initial conditions. You don't have to run it. If you don't run this program for initial condition, it starts from no waves anywhere. So you can start from a flat C, or you can give it some initial conditions like Jones-Swap spectrum or a Gaussian spectrum in space and time, and all that stuff. This is done by W3 STRT, and as a result, that will produce a file called restart.w3. And so the other way to get a restart file is to actually run the model, and at the end you can generate a restart file. And typically you can have restarts at different time steps. So the first restart file will be called restart001.w3, then restart002. And then if you want to start from that restart file, just move the restart file to restart.w3, and that will be the actual starting file. All right. And then you just have to give some basic input information in shell.inp. So this is, you have to tell the model it's using some forcing field. Are you using some level, some current, some wind, some ice? Now we also have some mud parameters and some ice thickness and flow sizes and ice rheology and some other crazy ice parameters. All right, and then you give it the beginning and the end of the runtime. So say you want to start on January 1st, 2008, and you run for 1 month, for example. Then you give it at what time you want the output, and there's 6 different type of outputs. And yes, and if you want to make some tests, you can just say, okay, I want to run academic test with a constant wind. With uniform, and then you can, if you have the uniform wind, you can specify this uniform wind at the end of the file. All right, so the output that you can do, so here it says 6, actually there's 7, and the 7th is for the coupling. And Mikkel, you'll be showing that tomorrow, right? The how we define the parameter for coupling. Okay, so I'll only talk without coupling, it's only 6. So the first type of output is a grid of output fields. And when, for example, it's a map of wave heights, of mean periods. It can also be a map of the full frequency spectrum. But if you want to do that, you have to specify some name list parameter that you want to have this type of output, because that is allocating a big chunk of memory to store this. So we don't do that automatically, otherwise it's just using too much memory. So if you want to have like spectra output on the entire grid, you need to change the out_s name list, and it's all in the input file for W3 grid. You have to do that before this. But yeah, all these grid fields. Then you can also request full spectra at some points, and you can have as many points as you want. So these days in our global model, we have 13,000 points. That's a lot of spectra to carry around. You can have output for nesting, other high-resolution grid. You can generate some restart files. You can generate some spectra along predefined tracks. And you can also output partition spectra. Actually, this stuff, I've almost never used it. I always get my partition through this one. So you can get the partition information through this one. If you do that, you'll get really the full partition data, not just the first 3 or first 5 partitions. You can get like all the stuff. it is in some funny format, but yeah. And Mikael, by the way, the tracking of the partition is using, I think the tracking was using this one, but I think now it's also using the grid output, but I'm not sure about that. For partition data. Okay, so you have all that information, the moddef file. This one is not needed. If you don't have it, it will still run. And then you call the executable W3 shell, and the output is, oh, very important, you get a log file, which is very nice way to know what's going on, if the model is actually reading the input, if it's producing the output, if it's running properly. So it's incremented at every time step. You can check what the model is doing. It's a very small text file. Then, oh yeah. And then you have all the different output files. And then on top of the log file, there is also information which is generated what's called the standard output. So if you just type it in command line, the standard output is a screen. What I do with all this program usually is I move the standard output to some output file. So I will just type W3 shell and then superior to W3 shell.out. So I keep track of what's going on, especially for the grid, W3 grid, so that you actually know what the program has done. So we'll do that this afternoon. And then you get all these different outputs. So the restart files, so they have some numbers. So you can have up to 1,000 of them. The nest files also for the different grids. So you can nest many grids. So it's going to be up to 1,000 grid if you're crazy. And then you have some output. These are binary output for the gridded parameters. This is for the point output, the track output, and the partition data. So all these files are something.ww3. And as I said, if you want to start from this for the next run, you just have to rename this file. You move it to this name, and then you can start with that one. And we have a small script somewhere to actually get the date of the restart file, because what happens pretty often, you save this file, and it's for some day, so it's going to be January 2, so January 1st, and you never know which date it was. So either you can run the model and it would tell you, okay, it's the wrong date, sorry, I cannot run, or you just run the small script and give you the dates, and then you can change the date in the shell.inp, because the date in this file, the starting date has to match the date in the restart file. Otherwise, the model won't run, which is a safety feature. All right. And the raw data. Okay, so the output files, this outgrd, can be a very big file. It contains all these parameters you want. And typically, you want to convert that to something you can use. So you can use either GXOutf or grads. For NetCDF output, you're going to use W3 OUNF, and these are similar to the ASCII text output with OUTF. So this is the way it works. So you can replace this thing with OUNF or NetCDF, and you get some output, which is a bunch of files. So in the case of NetCDF, just some .nt files, and so typically, yeah. So the small stability. Yeah, I should have had one slide for that. So in NetCDF, in order to avoid making very big files, like if you run 1 year of the model with all the variables together at each time steps, we've defined some way to slice the files in time. And so, for example, if you want to have one file per month, you have to say that you're going to use the file name has a date with 6 numbers. So it's going to be the 4 numbers of the year, 2010, for example, and then 01 for January, and then 02 for February. So it's going to jump for the first file. It's going to be 2010.01.nt, and then after the end of the month, we'll go to the next file and so forth. So, and if you want one file per time step, just specify the number of, I think it's like you put 10 in the size of the file name, and it will make it 1 for every hour or whatever. So that's one way we found to be able to slice the NetCDF files in small pieces, and then also NetCDF, you can also have either all the variables together, and that could make very big files, or you can have one file per variable. And this is what we chose to do for our FTP, because we don't want, people would just want the wave height, they don't want to download like 30 different variables they don't care about. So at some point, we'll move all that to a proper OpenDAP server, but somehow never found the time to do it. Okay, so that's some example of using GRADS, which is NCAR graphics plotting software, which is used at NTEP for their website. Among other things, that's a case of the Gulf of Alaska, and so it's just a grid up there, and you can see the wave heights and some wind and wave directions. And that's yeah. Okay, so then you have the point output, and the same kind of story. You run W3 out P. You just specify which point you want. Of course, you need to have the same point as you had in shell, because it's not going to, it will not invent new data. So if it's not stored, you won't get it. But from the list of all the points in the file, you can select which point you want and which time step you want, and you get some output file, which can be either a SNETCF file with OUNT or some output. Here it's going to be some ASCII funny files. And this is what you can do. Oh, and the very important thing also, you can also expect the source terms. So the source terms are not stored during the run, but they are recomputed on the fly. When you have the spectrum, it will call again the source term routine and recompute the source term that correspond to the spectra. So if you want to understand, what's going on in the spectra, so you get here's the spectrum. Here, that's a dissipation term. I guess this must be some nonlinear interactions. I don't know what that is. Oh no, it's actually written on top of it. This is wind source term, total source term, and nonlinear interactions. So this is a sum of all three, and that's the dissipation one. So if you want to know from NetCF or from ERA Interim or whatever you want. And you can, when you force a model, it's actually a good thing to also output the forcing, so you can check that the model has been reading the forcing as you want. Because sometimes, especially in the old days with the ASCII files, you can flip the grid upside down or left and right, and you get wind over land instead of not in the ocean and things like this. So it's always a good thing to check the output. So you just output the forcing, so you request to have the wind output and the current output, for example. So you can make sure that the model is doing what you think it's doing. And that's it. Yeah. So if you have some forcing fields, you have to transform them into binary, because WaveWatch will not run directly off the NetCF files from the UCMet office or whatever you want. So you need to pre-process them. For ASCII files, it used to be a pain because you had to first transform the grib to ASCII and then run W3 prep. So now you can just transform the grib to NetCF and run W3 PRNT. We've been adding a few features to allow funny NetCF variables. So because for us it was normal that people would have longitude and latitude in their grids, but it turns out that some people have INJ or some other names. So you actually can specify the name of the coordinates inside of the input file, and normally WaveWatch will be able to pick up the right variables in your file. And if it doesn't work for you, just tell us and we'll add some things like, of course, people also have, it's not having a 2D grid of wind. Some people have a 3-dimension grid because they have a level dimension and things like this. We keep adding more features to make it sure it works with more data. And then prep or PRNC will generate depending on what type of data you provide. So it will make a binary file called current.w3 if it's current, level.w3 if it's a water level, wind.w3 if it's a wind, and ice.w3 if it's ice concentration. If it's the ice thickness, it's going to be IC1. If it's the flow size of the ice, it's going to be IC5, and so forth. And that's pretty much it. Yeah, and then to actually run the wave model, it can run, yes, with the moddef, the restart file, but on top of that, you can add all these forcing fields, which are optional, and then the model will run and produce the output. There was something I wanted to say here, but I forgot. Okay. Okay. Well, that's an old command. So now there is some NetCDF. So NetCDF is not part of the main code. And the reason with that, we didn't want to have too much library dependency. So the idea is that even if you don't have the right library for NetCDF, you can still run WaveWatch and have ASCII output. But of course, it's more convenient to have NetCDF output on grid output because the files will be smaller and easier to handle. Nesting. Yes, so if you do nesting, essentially it's a one-way forcing. You have a parent grid and child grid, and you're providing boundary to the child grid. And the difficulty, so yes, you can set up, as many child grid or up to 1,000 child grid as you want. And the definition of the boundary points is all done in w3grid.inp. And that will result, and if you do this right, and you run w3shell.inp, it will generate a file called nest something.w3, and that nest is what you need to force at the boundary. So this is one option. As I said, the other option is to have point output, so you can have NetCDF spectra, and then you can combine these NetCDF spectra using w3 BOUNC, so for boundary NetCDF processing, and that will pack all these NetCDF spectra in a nice way to make the nest file. And I think we have some example of that. Blah, 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 nesting, nesting. I think I'm just tired of nesting. So, okay, so yes, you can have the nest file on top of that from the parent grid, and this grid can make some child grids. You can have different nesting levels. All right, final remarks. Right, so one of the difficulties is this time step that we discussed quite a bit before. Again, maximum time step, the CFL1, the refraction, and the minimum time step. You don't have to worry about the short waves, high frequencies. The time step is going to be adjusted, what you said before. And also the current is taken into account. So it's only, you really have to compute what should be your time step according to the CFL without any current, just propagation at CG, which is the caveat I made that if you have a grid which is regular in longitude and latitude close to the pole, the meridians go together, and so the spatial step gets smaller, and so this is this smallest spatial step that you have to take into account. Here we go. Oh yeah. In some tests, the output time step for some files, especially the restart file, is set to 1 second. If you copy this into your configuration, it's going to make a restart file every 1 second, which can be a couple of gigabytes. So if you run a 1 day with that, well, first of all, there's a limit of 1,000 restart files. So 1,000 times a couple of gigabytes is some terabytes. And then chances are your disk is full. Okay, so you may want to be careful about the time step for the output. If it's too small, just filling up this for nothing. There's also some examples with some Gaussian spectral correction when you use PR2 for the propagation. No, yeah. No, I think now it's going to be, yeah, so PR2 is a Gaussian spectral correction, and then it's, yes, use UQ or UNO for the second order or third order. Anyway, there's some numbers that's finding the swell age, so it gives you the smoothing effect because it's going to smooth the energy along the wave front, so perpendicular to the wave propagation. And somehow there are some tests with some very small value for that. So I think it's in the time stepping thing we're going to do this afternoon. And so if you actually use these very small values, it can make the scheme unstable. That was just some remark on that. And yes, if you're running out of memory, you get some bad crashes. And the running out of memory can happen, especially if you're requesting spectral output on the grid and stuff like that. So you may want to monitor the memory usage of your model because it can, it may crash and you don't know why, and it's a bit annoying. And that's it. That's all I have. So running the model, get the theory. So now we just have to practice. And so there are different files, the W03 something. Each has its own input file, and you run it to get some output, and that's the story. So you're ready to try? Okay, so I guess we can just go for, or you can go for lunch because I have some other things to do. So I'll join you back at 2 p.m. on the other side. So Mikael will take care of everything. Yeah, you can have lunch here, and then this afternoon, or after 1 p.m., you can go to the side.